In this video, we will cover the Media Access Control Protocol employed by Ethernet CSMA CD. We covered the basic idea behind CSMA class of protocols, basically the listen before talk. Ethernet MAC employs one persistent CSMA. Now, if you have followed one persistent CSMA in detail, this thought should have occurred in your head. What? One persistent CSMA? That is such a horrible protocol. It's so greedy. Its performance at high loads is so poor. How could they standardize such a protocol? So how well Ethernet performs? This suspense we will resolve by the end of this video. A point to note here is that Ethernet MAC of CSMA CD is applicable for bus topology as well as star topology, but in star topology this is applicable only for shared mode or this half duplex mode. The CS in CSMA stands for carrier sense. The MA stands for multiple access because there are many nodes trying to compete for access to the channel, and the CD here stands for collision detection. So in human analogy, if more than one person is talking loudly at the same time, then no one can understand what is being said. Then what is the best strategy there? If it's the Indian Parliament setting, people will still continue to talk, but the best strategy is to stop talking, giving an opportunity for one of them to talk. So this reduces wastage of resources. So in computer networks, if two arrivals happened at the same time in one persistent CSMA, they're both going to start transmission and they're going to collide, and this packet transmission can happen for a really long time depending upon the size of the packet. Now collision detection can happen rather fast. This can happen immediately after the packet transmission. Now if you abort your transmission at this instant itself, all this you are going to save. This wasted resource you are going to now save. So that's the basic idea of collision detection. Going ahead, I'm going to employ some numbers to demonstrate concepts. These numbers are applicable to 10 Mbps Ethernet, but the concepts as such are applicable to any version of Ethernet that employs CSMA CD. Since collision detection is the big feature we are adding, let's understand this in a little bit more detail. So what are the cases under which collision occurs? Remember, we are dealing with one persistent CSMA. I claim there are three cases. Try to think of these three cases. The first is rather a straightforward case. For example, there is a transmission happening on the channel and there are multiple arrivals during this duration. All of them are going to wait for the transmission to end, and because it is one persistent, they will attempt transmission right after this and they're going to collide. This can be a rather rare case, but it is still possible that two arrivals happen on an idle channel at the same time. So both nodes will transmit and then they are going to collide. The third case is a bit tricky. I claim that two stations attempting transmissions at different times on an idle channel can also collide. How can this happen? What characteristic of the channel can be responsible for this? Propagation delay. So this figure explains it in action. So we have these four nodes N1, N2, N3, N4 connected to the Ethernet, and let's just assume that they are separated by distance x. And let's also assume that t is the time it takes for the signal to propagate distance x. Now when node N1 begins transmission at time 0, for this first bit to propagate over this Ethernet, it's going to take some time. So it is going to reach N2 only after time t, and it is going to reach N3 only at time 2t. Now if you see N3, it has a packet to transmit, let's say at t over 2, and at that time when it sends the channel, it did see that the channel is idle because it has not yet received the first bit of N1, which doesn't come until 2t. So it will assume that the channel is idle and it will begin transmission, and as you can see, this transmission will collide with N1's transmission. So N1 and N3 are transmitting at different times, but still their transmissions are colliding. If you also notice, each of the different nodes are detecting collisions at different times. For example, N3 is able to detect collision at this time when it receives N1 signal, and at this time N1 still hasn't detected the collision. It is detecting collision later when it receives N3's signal at this particular time. Whereas N2 could detect much earlier because it is in between N1 and N3, so it detected collision at this particular position. Well, actually you cannot quite detect collision with just one bit. It does take for you to receive certain bits to detect collision. So this is being indicated by this. But as soon as you detect collision, both the transmitters are going to stop transmission. So even though this could be a very large packet, it would have gone on. But since they have detected collision, they are stopping the transmission at this particular point. And after this point, they send the jamming signal. Both of them. That is both the transmitters. A bit more detail on collision detection. This collision detection is typically done by the hardware. As I mentioned before, the sender, as it is transmitting on the link, it also receives and compares it with what was being sent. If they don't match, it detects that there is a collision. This propagation delay as part of collision detection can significantly impact efficiency. Now, if the propagation delay was large, would the efficiency be better or less, and why? So the longer the propagation delay, the more time it will take for nodes to detect whether the channel is idle or busy, and they will start transmission because they will think it is idle, and this leads to higher chances of collision. Now, if you have a network diameter of length L, that is the maximum distance between any two hosts A, B is given by L, what is the worst case delay of detecting collision? That's right, one round trip time. For example, A send the frame. It takes some time for these bits to reach B. So this is one-way propagation delay. And let's say just before the bits reached B, it sensed that the channel was idle. So B also transmitted, and it is going to take some time for these bits to reach A, and this is the one round trip time, twice the propagation delay. So as soon as a collision is detected, all senders who are responsible for the collision send what is called a jamming signal, which is of 32 bits. Why such a jamming signal? If you remember the frame structure of Ethernet, there is a 64-bit preamble followed by the header. Suppose A were to send a frame, the first bit reached B at this particular time, and prior to that B sends the channel to be idle and it started its own transmission. So this happens somewhere in the preamble. Now preamble is used for synchronization, and this is what helps other nodes to even receive data. So you have to send the preamble, you cannot stop in between. And if B were to stop right after transmitting the preamble, which is 64 bits, so it will send the preamble, so this is kind of going to the other end A. Basically A is going to receive only 64 bits. Now this is typically not enough for A to detect a collision. It needs an additional bits, so you send additional 32 jamming bits so that A can detect the collision reliably. Basically, jamming extends the frame of B so that A can detect collision properly. We talked about this before. I mentioned earlier that Ethernet frame sizes have to have a minimum size of 64 bytes or 512 bits. Of this, you can permit 46 bytes of payload and 18 bytes of Ethernet header. 46 bytes of payload is higher layer data like IP. What if this higher layer sent a payload data that is less than 46 bytes? In this case, you have to pad that payload till it reaches 46 bytes. By padding, I mean you add redundant zeros, dummy zeros at the end, such that the Ethernet frame size, including the header, reaches 64 bytes. Now, why do we have such a restriction on frame size? This has to do again with collision detection. So look at this figure and tell me, why do we have a minimum frame size restriction in Ethernet? If a host has to detect a collision of the packet that it has sent, it has to transmit for at least one round trip time. And this round trip time for 2500 meter long cable with 4 repeaters turns out to be about 51.2 microseconds, and at 10 Mbps this turns out to be 512 bits. Suppose node A has only 100 bits of data to send, so it started the transmission, and node B, which is at the other end of the network, listened to the channel. It found it to be idle just before the first bit came, and it also started transmitting. And for this packet to reach A, this duration turns out to be 51.2 microseconds. In bits it corresponds to only 512 bits. Now node A, after it transmits the 100 bits, here if it were to stop, then it will not see this bits, colliding bits from B, and thereby it will assume that everything went fine with its transmission because it did not see any collisions during the period of 100 bits. This won't do, so you have to continue to transmit for at least 512 bits so that you can detect any collision that is going to impact the transmitted frame. While we are here, let me also emphasize that the maximum number of hosts that Ethernet can support is only 1024 hosts within a collision domain. If there are more nodes than this, that means the load becomes high and the chances of collisions becomes more. Whenever an adapter has a frame to send, first it has to sense the channel, and it has to sense the channel idle for 96 bit times. So this corresponds to 9.6 microseconds if we are dealing with 10 Mbps Ethernet. Why this wait? Just because it gives an opportunity for the receiver to process the previous frame before it is ready to receive the next frame. If you remember, when we talked about the frame structure of Ethernet, I was mentioning an interframe gap. So this corresponds to the interframe gap. Now as soon as it finishes this checking for idle time of this duration, it starts transmission. But if it found the channel to be busy, it waits until the channel becomes idle and then additional 96 bit times, and then it is going to transmit. Because it is one persistent, there can be collisions. But if no collision is detected as part of the ongoing transmission, the frame transmission is deemed successful and the adapter is done with that particular frame. But however, if it detected a collision during the transmission of the frame, the adapter will stop the transmission, send the jamming signal, and enter what is called exponential backoff. Basically, this dictates what is the random time the adapter has to wait before it tries to retransmit this particular frame again. So here is exponential backoff details. So when you are transmitting a frame after the nth collision, you basically wait for k times 512 bit times, where k is chosen random within this interval, where this value m is given as minimum of n, 10. So let me give an example. So for example, a frame was transmitted, it suffered a collision. So that was the first collision that it suffered. Then this node is going to choose a k between 0 and 1. If it chose a value of k 0, then it is going to try to attempt transmission of the frame right away after waiting for that 9.6 microseconds. Whereas if it were to choose a value of 1, it will wait for 51.2 microseconds and then attempt the transmission. But during this time, if it were to detect that the channel was busy again because someone else chose a value of 0, then it will again have to wait till the channel becomes idle and then repeat the process. What if it transmitted again and that also suffered a collision? This will be the second collision. In this case, the node will choose a value of k between 0, 1, 2, 3. And this goes on where after the 10th collision, chooses k between this value, and then it keeps this range constant till the 15th collision. In other words, the maximum number of transmissions for a frame is restricted to 16, which involves one original transmission and 15 retransmissions. So as you see, the size of k is growing exponentially after each collision. So why this exponential backoff? In other words, what is k trying to capture? Basically, K is trying to capture the current load. If the load was low, small values of K will suffice because you don't really have to wait for a really long time to access the channel. But when the load is high, this is going to result in lot of collisions. And if you were to choose a small value of K, for example, if there are 10 nodes trying to transmit a packet, and if you chose K is equal to 0 and 1, everyone is bound to collide. So this won't do. You need a much larger K. A given node has no way of knowing what the load on the channel is. It has to get this feedback from the channel itself, the behavior it is observing on the channel. If it is experiencing lot of collisions, that means the load is high, thereby it will start choosing a larger value of K. If it is not experiencing that many collisions, that means the load is less, thereby it chooses smaller value of K. And where did this 512 bit time come as part of exponential backoff? Basically, this gives an opportunity for a node which chose a lower value of K to transmit without collision. For example, node A chose a value of K is equal to 0. Let's say node B chose a value of K is equal to 1. So K has started its transmission and it's kind of ongoing. Now B is going to wait for 51.2 microseconds before it is going to listen to the channel to decide whether it is idle or not. The why it has to wait for this time is it has to allow for the propagation delays, in other words for A's bits to reach B so that B can detect that there is an ongoing transmission and not transmit. This value ensures that all nodes in the network can hear A's transmission and thereby not transmit. And this happens if they wait for at least 51.2 microseconds. So what is Ethernet's efficiency? Don't worry, I'm not going to derive this expression. It turns out that when there are large number of nodes with large number of frames to transmit, the efficiency is a function of the propagation delay. This is one-way propagation time between two nodes in a LAN and the time it takes to transmit a frame. If this propagation delay is tending to 0, what does efficiency become? So in this case, the efficiency is tending to 1. What is the reason for this? This is because you are now able to detect collisions rather instantaneously and thereby you are not wasting the channel resources. That leads to very good efficiency. Similarly, if the transmission time TTX is rather large, again the efficiency tends to 1 because you are using the channel for doing useful work. So by carefully configuring the Ethernet, we can maintain very high efficiency. What do I mean by configuration? Basically by choosing very large frame sizes. So typically Ethernet uses 1500 bytes. Also ensuring this maximum propagation time between two nodes is small. So typically you operate under few hundred meters. That is the max distance. So this efficiency equation was derived under large number of nodes. Naturally, when there are more number of nodes, the chances of collision are higher. Again, you can maintain high efficiency by ensuring that you have fewer number of nodes per segment, by which I mean within the same collision domain. Even though the maximum limit is 1000 hosts per collision domain, typically Ethernet operates under 200 hosts. So if you did all this, you can always maintain an efficiency which is greater than 85%. To summarize, the CSMA family of protocols improve upon Aloha. There were two persistent and non-persistent CSMAs and there are trade-offs involved here. Ethernet MAC employs one persistent CSMA and adds this feature collision detection to improve performance. And as you saw, if your collision detection is very good, you can maintain your efficiency rather high because you are not wasting the resources anymore. Now this collision detection definitely needs additional functionality in terms of hardware support. It also places restrictions in terms of the length of the cable, frame size, so on, as well as the number of hosts that can be part of the particular system. but by appropriately configuring Ethernet, you can achieve good performance. All said and done, within a collision domain, the maximum number of hosts you can support or the network diameter that it can take is rather restricted. If you want more number of hosts and larger network span, you need to do something different, that is Ethernet switching, which we will cover in the near future.